Hi, everyone. So we are doing the Ohm's Law post-lab discussion and also the introduction to series and parallel circuits. So if you were absent due to A/B testing, this is going to cover everything you need to know to understand Ohm's Law, the formula we're going to use, and also the information you're going to need to do a lot of the worksheets that are going to be coming up as homework. So first of all, if you did the Ohm's law, then you should have gotten a graph like this. Voltage versus current. Voltage is in volts, current is in amps, and it should have been linear with a y-intercept at 0. We used a simulation, so there's no room for error. Everyone should have gotten a y-intercept of 0. And then part of the analysis was to try to determine what this slope represents. And you should have seen a very clear pattern that the slope's value was always equal to the value of your resistor. So in the beginning, you started off with the default of a 10 ohm resistor. Your slope should have been 10. And then when you increased it to 2 resistors, it should have been 20, and your slope then should have been 20. So if you notice that pattern, and you may have used a different size resistor, that's totally fine. In the end, it should have been the exact same value as slope, and I hope you saw that pattern. So slope equals the resistance. And when we write out our very general equation with no values and just the variable representation, I'm going to start with y equals mx plus b. I know that the b is my y-intercept, which is 0, and with my 5% rule, I already know that that's going to drop. And so I'm going to end up with a y variable of voltage is equal to a slope variable of resistance. For your mathematical model, you would have put in your value of 10 or 20 or whatever resistance value you'd put it as. But I didn't tell you this, or I might have briefly mentioned, but the resistance value is in ohms. It's that Greek symbol omega. And so you're going to have to memorize these new variables as well. And then I need to, so this is my y, this is my slope, and then I need to multiply it by my x, and that is going to be my current. So this gives us our Ohm's law equation, and you're going to see this in your physics helper as voltage V equals resistance R times I current. It actually is written as VIR rather than VRI. Not sure why. I think it rolls off the tongue a little bit better. And you're going to start using what we call the VIR triangle, because you're going to be solving for any of these different variables, and you want to make sure that it's easy to solve without doing too much calculation. So when I ask you for current, you cover up the I because that represents current, and take your voltage divided by resistance. If I ask you for resistance, you're going to take voltage divided by current, and then if I ask you for voltage, you're going to just multiply current and resistance. So the VIR equation, you probably saw it in worksheet 34-2, is going to be a really valuable tool to use when you're doing these problems. Okay, so let's get into some of these definitions. I know I already went over the basic Ohm's law equation. So this right here is Ohm's law. We use it in circuits when we want to determine how much current is going through a wire, how much resistance is device giving, and to make sure that we don't short circuit our power source. All right, everyone. So as I stated in Ohm's law, we've got current. Electric current is the rate of flow of charges. We use E negative to represent electrons. And the more electrons you have flowing through a wire, the more current you have. The variable we use to represent current, as I've stated, is the variable capital I, and the unit that is used is amperes, and it measures the amount of coulombs, which is the amount of charge per second going through a wire. And you can also represent the amperes variable as 1 coulomb over seconds instead of 1 amp. But generally amp is, or capital A is the variable we use. Either one works for me. The resistance is the amount of resistance a resistor, and this is what resistors look like, or a device like a light bulb will cause to a current. You can think about it as toll booths when you go through traffic. The resistance is what slows down the traffic. And if you put any device or any sort of resistor into a circuit, it'll slow it down. Generally, you want that to happen to avoid short circuiting. And the little colored lines here represent the amount of resistance each resistor is giving. So they limit how fast electrons can move through a circuit, a closed loop, a wire, very similar to metering lights or toll booths. So you're going to see me use a lot of analogies to represent the different aspects of Ohm's law. So current you can think of as the amount of traffic and how it flows. I also like to think of current like a river, how fast the water flows down a river. When I think about voltage, I like to think about it in terms of energy. So when I talk about a voltage source, it's the amount of energy that is stored there. And when we've talked about energy, we've talked about energy in terms of gravitational potential energy. So I like to think of voltage as the amount of gravitational energy held in a system. So if you think about all of this water as water molecules as charges, if charges are held up high, then it's going to have high gravitational potential energy. You can think of this as high voltage, and then it's going to have room to flow downward due to gravity, or room to flow if there's a big buildup of electron charges. So the pipes here you can think of as resistors. How wide or how narrow the pipe is would either slow the charges down or speed them up. And as I stated, current can be thought of as the rate of flow. So we've got more flow for a wider pipe, less flow for a skinnier pipe, and that means that we have high resistance for the skinny pipe and low resistance for the wide pipe. And then we can also think of resistors as something like bottlenecking, where you've got some sort of tightness in your pipe that slows your current down. So if we put all of this together, high potential energy, or we can call this voltage, high voltage, is going to be higher gravitational potential energy. It's a high buildup of charges, and all those charges want to get away from each other. Here, it's a high vertical height, and so all the water wants to flow downward. When we allow it to flow, then we've got current. And when the current is going through this wheel, it can actually do work. So you can think of this wheel as a resistor. And we know that light bulbs or devices are also types of resistors, and those devices can do work. Light can exert light energy, transfer that electrical current into light energy, and it can also take your computer or your toaster or your hair dryer and create work out of the electron flow through that device. And then once it goes through that device, you've used up some energy and you've got low potential energy. So your battery has then done something called a voltage drop, where you've got high voltage here and then it's dropped to a lower voltage or zero voltage once it goes through the circuit. Okay, I've already talked about Ohm's law. It's V equals IR. You've got your current, which represents I, your potential difference, also known as voltage, as V, and then you've got your resistance represented by R. So memorize these variables. I for current is the only one that's not as obvious. And then think about the proportions. Obviously, if the current increases, then the voltage increases. The faster your charges, the higher your, or the more voltage you have, the faster your current. If your current increases, then your resistance decreases. Or if your resistance increases, your current decreases. The tighter your pipe, the slower your charges are going to go, or the more toll booths you have, the slower your charges are going to go. And then we've got voltage and resistance directly proportional. So all of these proportions, you guys are familiar with working with proportions. So I hope that that is a concept that's easy for you to translate into Ohm's law. Okay, resistance, I've talked about this, but let's go over it again. Resistance is capital R measured in ohms. That's this omega symbol. We've got potential difference, or actually this one is your potential difference or voltage. So that one is measured in volts, capital V. So notice how the unit and the variable are the same. And then you've got current, which is represented by capital I, measured in amps or amperes, capital A. Okay, so your resistors generally look like this, as I've stated. An ohmic resistor will have a direct proportion to voltage, but you can have variable resistors, which tend to have an exponential graph versus a linear graph. And all the ones that we're going to work with in class are going to be ohmic resistors. So they're all going to have that linear relationship. And so Ohm's law works for those type of resistors. These are the symbols you want to be familiar with. These especially, which is your battery, the negative and the positive side are short and long lines. If you have more than one short and long lined up together, that means that there's more than one battery lined up against each other. And so you want to make sure to count each individual battery and add up the voltage in total. The resistor is this squiggly line. I think they use that because it obviously, if current goes through it, it will slow it down through this path. And then you've got a switch, which obviously looks like a switch if you open and close it. Light bulbs tend to look like this. They have the kind of filament shape on the inside. Ammeters and voltmeters. Ammeters you want to connect to the circuit itself to make one closed loop with the ammeter, but a voltmeter you want to connect each end of the voltmeter to opposite ends of either a resistor or a battery to measure voltage. Now let's get into series and parallel circuits. So series circuits are when you have an electrical when you have a loop with all the electrical components attached to that one single loop, and you only have one current because the current only has one path to travel through, and so it remains constant. In a series circuit, you add the resistors in series, so simple addition, and when you increase resistance, we know it decreases current. So this is what it looks like. You've got a battery, and you've got one loop with all the resistors attached to it. Again, you only have one loop, so that means you have the same current. And anytime the resistors are lined up back to back, you add the resistance values together. So I wanted to have you guys do this one problem down here at the bottom. So we've got a circuit with 10 ohm resistors. I know it's hard to see here, but it's asking what is the total resistance? Well, if this is 10, 10, and 10, I just add 10, 10, and 10, and I get a total resistance of 30. If I have a current of 0.45, that's the same current that goes through the entire wire because there's only one of them. And then I can solve for voltage by doing my V equals I times R. So if I want my total resistance times my current, I would do 30 times 0.45 to get my voltage. And again, current stays the same. Here in a parallel circuit, you've got each component connected in its own individual loop to the battery, which means the battery is powering each resistor independently. And so each resistor is going to get the full voltage of this battery. In parallel circuits, the voltage stays the same because they're all individually connected to the battery, again, in their own separate loop. So voltage is constant. And the resistance is going to be a little bit harder of a calculation because it's not going to add up in resistance. Because each resistor has its individual path, it's actually going to decrease the total resistance. So to get your total resistance, you would do 1 over each resistor value. So take the inverse, add them together, and then whatever your total is, you're going to take the inverse of that, because if you notice the equation, 1 over our total is the inverse of the individual resistors added together. So if I were to tell you each of these resistors is 10 ohms, you would do 1 over 10 plus 1 over 10 plus 1 over 10, which is obviously 3 over 10. But then that's not your answer, because the answer there is 1 over our total. So I would take 3 over 10 and flip it, and my total resistance would be 10 over 3. So 10 thirds would be my total resistance. My current, as it comes out of the battery, is going to split out of these individual pipes, which means that the current going through each resistor is not going to be the total current coming out. So you're going to have different current values for each resistor depending on what that resistance value is. For this one, because they're all the same resistance, then the current going through it is all going to be the same, but you're going to have much more complicated scenarios where each resistor is different and you have to calculate the individual currents themselves. So I already talked about adding resistors in parallel. It actually decreases resistance, and this is your equation. All of this is in your physics helper. And again, the voltage stays the same simply because the total voltage of your battery is going to be the total voltage that goes through each resistor. So if I had a 5-volt battery, then I would have 5 volts going through R1, 5 volts through R2, and 5 volts through R3. All right. We're not going to have you type into the chat, but I want to talk about advantages and disadvantages. So first of all, the advantages of having a series circuit is that you have less wires to work with. You have one nice clean loop, but the problem with it is that if you break a bulb, all of the bulbs go out, or if you have appliances in series, all of your appliances go out. So you would not always want to set up your household appliances in a series circuit. If you burn out your toaster, then your oven's going to go out and your refrigerator is going to go out, for example. There are disadvantages to parallel circuits, though, even though it seems like a great advantage to be able to have individual light bulbs in parallel. If one light bulb goes out, the others stay on. The disadvantage to that is that you're going to have a ton of wires. So a lot of Christmas lights like to be in parallel, but it isn't quite practical to have all of the Christmas lights in parallel, simply because you can't have a gazillion wires going through your individual Christmas lights. It's not practical. So less wires for series, but more effective if one appliance goes out. For parallel, you don't have all of your appliances or all your light bulbs go out. So some examples: series circuits would be lamp dimmers. If you dim your switch, then it's going to obviously affect your lamp. Safety devices like fuses or circuit breakers are all connected in series, so that your breaker will go off if you've got too much electrical energy going through your wires. And then you've got parallel circuits where you've got car headlights in parallel. If you turn one, if one headlight goes out, the other one will not. And then most houses and some newer holiday lights are in parallel series as well. A parallel circuit. So this is what a series circuit looks like. They are all connected in one loop to the battery or to the voltage source. This is what a parallel circuit looks like, where you've got each individual light bulb connected to the voltage source. And then I want you to notice the difference. Series gives off much less light because the total resistance is higher, versus parallel, which when you add up the resistors, remember you're adding the inverse values, so it ends up being a lower resistance. And the way you can think about it is like toll booths. If I had 3 toll booths in series, it would really slow down traffic. But if I had 3 toll booths in parallel, it allows traffic to flow a lot easier. So some good analogies to relate to series circuits and parallel circuits. All right, so this is how you would solve circuit problems. I generally like to use vertical circuits where I can see a voltage drop through R1 and a voltage drop through R2. The current stays the same, the voltage drop changes, and the total resistance is the sum. With parallel, you've got a voltage drop through R1 of the total voltage of the battery, and the voltage drop through R2 is going to be the same as the total voltage of the battery as well. And this one is adding up the inverses. I apologize that you can't see it, but you have the equation in your physics helper. So when you do these problems, there are these VIR charts that you can use. Generally, you want to have your resistors labeled in values of R1 and R2 and so on and so forth, however many you have. In a series circuit, the current stays the same. So if you can find the total voltage of the battery and the total voltage of those 2 resistors, then you could solve for everything else in the chart. Same with parallel, except for this time the voltage stays the same. You want to add up your total resistance using the inverse sum, and then you can find your current from the remaining values there. It's kind of like a puzzle, and I like to relate it to Sudoku. Some students find it fun, but other students find it complicated. So we'll step through this. We'll go through this step by step together very carefully. Thanks, everyone. Hope I didn't bore you too much, but we'll do a lot of practice on this before the test.